Okay, let's continue. So chapter 7, it has both information criteria and cross-validation. But since the book was published, we've done additional research on these topics, and now so we found out a way to do cross-validation so that we can do it more reliably than with information criteria, and there's a connection. I'll come back to that. But specifically now, section 7.2, it's better that you read this paper instead of this section because it has more up-to-date information and also a bit more clearly. There's also in that paper more about the model comparison, and in other papers so I'll talk more about specific model comparison cases next week. So there's more than in 7.3. 7.4 and 7.5 are kind of okay. I do mention the problem with the base factors also today, and then 7.5 is related to that. Instead of trying to do model selection between two separate models, we would prefer to do continuous model expansion, which would include these separate models as special cases. And then you can skip that example. There's also a link to this collection of videos and the slides for those, and a lot of different case study notebooks. So what I now talk today and is kind of what's also in this video I mentioned there, because this is not the first time I record the video in this lecture here. And then that specific video mentioned there, the second part, I will cover some of that next week. My background, how did I get interested in researching how to estimate predictive performance of models, is that I did these different projects with industrial partners, or in this case it was another doctoral student doing research on concrete quality properties, so that this shows a measurement of one of the concrete quality properties. So there was a different experiments of kind of the concrete quality depends on what kind of sand do you use. Is it natural sand or crushed stone? How much cement you add, different additives, how much water you add, and so on. And then one of the things is that how easy it is to work with that wet concrete. And so the measurement is taking a bucket of wet concrete and then turn it upside down and take the bucket away and then measure how much it slumps. If it's too wet, it slumps too much, so it's not easy to work with either if it's too wet, and then if it's too thick, it doesn't slump enough, and then it doesn't go to all the corners when you pour it. Of course, there are also other, like the compressive strength after 3 months of casting, which is important that whether buildings and bridges don't break. And so I was then making these Gaussian process predictive models to predict based on what was the recipe, what was the different mixture of natural sand and crushed sand, and then predict these different quality properties. And I was, of course, worried that if I now have this model and that the compressive strength is like this, I want to also know how big error I might be making when predicting certain compressive strength, that people don't make bridges based on my prediction saying that, oh, of course this will hold the load. And then I got interested in how to estimate these predictive performance and using cross-validation. The nice thing was that in the end of this project, we were able to make that concrete expert made then these recommendations based on the experiments and model which were able to reduce the amount of natural sand used in making concrete, which is very useful because the amount of natural sand is there's not much left sources, for example, in Helsinki region, and it's often important, for example, for the groundwater production. So there are many places where there would be nice natural sand, but cannot be used. Natural sand is good because it was already a lot of crust by ice age, so it already broke all the fractures inside the stone. And when making then artificially crushed sand, there's a problem that there's fractures in that sand, and then that's why people have been using a lot of natural sand, but then we were able to, based on this model, to show what kind of mixture of natural sand and what kind of these artificial sands can still make a good quality. It was last year, then there was in the news that there were one or two bridges that after construction they noticed that they are not actually that good, that they have to tear down those bridges before they are even used. And I was, of course, worried that whether it could be my fault also based on the predictive model. But it turned out that they had started using new additive. And this additive changed how the behavior, and they did not update the models. And so it was not my fault that a couple of bridges were now teared down. And they, of course, also the teaching is that if you change your data in the future, if you go beyond your training data, predictions are not valid anymore, so you need to take that into account. I've also worked with some health-related models. There's a web interface for calculating risk of cancer recurrence in gastrointestinal stromal tumor. And again, we would like to know beforehand how good our models are, especially if we are making decisions based on those. So another example why I've been interested a lot in these predictive performance. And as kind of mentioned also in model checking, that nice thing would be if we could just wait for the new data and do the external validation. But now with the there are different ways how we can approximate this external validation and what would be the expected predictive performance if we would wait for new data. In this concrete prediction, I was interested in kind of how big error there is, so I could report that, okay, with 95% of probability the error is smaller than this, and kind of the certain quantiles, that how likely it is that error is smaller than this. And this is kind of example of application specific, that it was related to kind of that, what's the safety limits, for example, the compressive strength. And in these different applications, it's important to use these kind of application-specific utilities and cost functions. They could be also then money. In medical cases, they are often life years or quality-assessed life years, etc. I'll talk more about, when we come to chapter 9, decision analysis, about the problems of choosing utility and cost functions and decision making. But then today in these examples, what I saw, and also what is enough for your project work, is that we use this kind of generic utility function. So if we make a predictive distribution, so that we predict that in future y, which could be, for example, that compressive strength, and then we predict that, okay, given this recipe, this kind of sand, the compressive strength is predicted to be in this range, and then we would actually make with that sand and that recipe the concrete and cast it and wait 3 months, and then we would observe that, okay, it was actually measured to this. We could then look what was the density at the actually observed value. And of course you can see that then this is in a way generic, that we would like to have observe something which is somewhere where the density is high and less where the density is low. And then it's common to take the logarithm. There's a couple reasons for that. Makes it easier to handle, and then it has some nice properties. And so generically this log score is useful. I'll have a bit more about that soon. So now today I'll go through what is cross-validation, a bit when cross-validation is applicable, a bit about how to make cross-validation fast. You can see smaller font for related methods, so information criteria and Bayes factor, a little bit about those. A little bit about the model comparison and selection, and then next week more about model comparison, model selection, more about model averaging and stacking. So when you're using in your exercises and project work Stan, you're likely to be then use also glue packets if you're using R. And in Python there's an RViz package which has this same functionality. And I will also then briefly explain different parts what we are reporting in this output. Here's an example that true data generating mechanism is now, there's a linear relationship between x and y, and then some randomness, so that in addition of the linear slope, given certain x, we are randomly generating y from this Gaussian distribution. And here's one example replication. Different x values, for each x value generated from Gaussian, which has the mean based on the linear slope, and then the same standard deviation in every place. And then we can fit a linear model there, and we see here the posterior mean. And it's of course likely that when we have a finite number of observations, that this posterior mean is not exactly the same as the data generating mechanism. Just by chance, the observations are just that now the slope is estimated to be slightly the lower slope. And then if we would have alternative data realization, same number of points, but just repeating the data generation, we might get different estimate. And this shows that kind of that always our estimates are somehow fitted towards the specific data realization. And then again we can go back to that first dataset, and we can also then illustrate the posterior uncertainty. So we have posterior draws here, shown as blue lines, and then it also shows that that because of the finite data, there's some uncertainty where this slope goes. And we can make also this posterior predictive distribution, shown with the now red line, the red curve there. And this is, of course, now based on integrating over the posterior distribution and then and so so that we have posterior distribution p theta given data x and y, and we can look at the predictive distribution. So y tilde is what we would kind of predict that the new observation, and now given that new x tilde would be 18, and if we would know theta, then that's certain Gaussian, but now we can integrate over theta and we get the posterior predictive distribution. We could wait and get new data, and you can see that now the new data is slightly different than, of course, than the previous, and now we could evaluate then these densities, that how high density we have for each observation. We can also now, before getting the new data, we can look at this for already observed data. So now this is one of the already observed data points. It was used to also when updating the posterior distribution. But we could also think that what if we would have fit a model without that point? You can see now that if we would remove that 18th observation, then the green line shows what would be the fit without that observation. And you can see that it goes further away from that data point. So with that data point, our fit, the red line, is closer to that, and without that, it's further away. So that's the kind of how much that one observation affects our posterior mean. And now we could then use this 18th point as a new data point for that model, that green model. So now we would have kind of we are left out one observation, so that we can now simulate that case that, we fitted the model with certain data and then test how accurately we can predict something which was not used to update the model. And in this case, it's just now showing the kind of how far it is. So what is the kind of the residual? So it's 2.2 away from the mean. And as an equation, so we have the observation, 18th observation, the y value for that, and then the expectation, the mean value for the predictive distribution, given that x tilde is 18, and we have data set where we now denote x minus 18 and y minus 18, all the other data except that 18th observation. And already we could use this now to compute root mean square error, r squared, 90% error, and the 90% error was something like I used in the concrete quality example, that we can give some mean prediction and then show how big error. We can see now that it's likely then that these leave-and-out residuals are bigger than the posterior residuals, because if we leave some observation out, it's likely that the model goes different direction. Just leave-and-out R-square specifically, there's a link to that if you are interested in. But instead of looking at this mean error from the mean, we are interested also whether that kind of the shape of the predictive distribution is good. And then we can also, now there's the red curve is showing the posterior predictive distribution, and green one is showing the leave-and-out predictive distribution. And you can see that that predictive distribution has also shifted a little bit. And then we would like to evaluate how high density there is with that left-out point. So here's the leave-and-out predictive distribution as equation. So we have the posterior distribution with all the other data points except the 18th, and the usual predictive distribution with x tilde at 18 and then theta, and then integrate over theta. We can compare now in a way that what is the effect that we left that data out. So if we would look at the posterior predictive density, so how high density there is for the 18 observations given the posterior predictive, the red curve. So we have density 0.07 and given that value, and then given the leave-and-out predictive density, we have now density 0.03. And so it's likely that when we use, so if we would use that 18th observation both to fit the model and to test how well we can predict it, we get usually higher densities. But if we don't use that observation to fit the model and then try to predict it, we get lower densities. But now, the good thing about looking at this predictive density is really that it is taking not just account where like the center point of the predictive distribution is, but also the shape, how the tail goes. And you can remember that we can't make far away points more, that if, or in a way that if we make this wider to make far away points more likely, having higher density, at the same time then we would make points in the middle have less density. So there's a balance. We would like to have really, we get the highest average density if all these future observations happen to have same distribution as our predictive distribution. Okay, so now we see that we can do these leave-and-out predictions for one point, but we can also repeat it for each observation separately. And this is showing what if we would take the certain observation, we would leave it out, fit model, form a predictive distribution, and then look at the density. It is then easier to go on log scale. So here I had the densities and then just taking logarithm of those, usually natural logarithm. But there's also not just because that it's easier in a way that we might have sometimes small densities that it's benefit to go to log score or the log scale. There's also other reasons for this. We can now take a sum of these log densities. If we would be staying on the original scale, then it would be a product of these densities. We would kind of think that, okay, each densities independent of each other, and then product in a log scale, we get then sum. And some of these, in this case, were minus 29.5. And this is now what we call in the book and in the paper and the Lua package, expected log predictive density from Lua. Leave one out cross-validation. And this is unbiased estimate of log posterior predictive density for new data. So in this kind of simulated case, if we would now simulate new data, this would be unbiased estimate of what would be the log densities for new data from our predictive distributions. We can compare this now, the sum of these individual log leave and out predictive densities. What if we don't take into that leave and out? What if we look at directly, we use all the data points for fit the model, and then we double use the data, so we now evaluate the density of yi given xi, and then the yi and xi are also there another time. We get something which is higher value, so we get higher log predictive density, higher predictive density altogether. And one reason for going to log score is now that if we now make a difference of these two, it happens to be something which can be sometimes called effective number of parameters, which is related to model complexity. In this model, we have intercept term, slope term, and the unknown sigma, how much the y varies given certain mean value. And so we have three parameters, and our difference between these ELPD Lua and LPD is close to 3. And this also shows now that this is the amount of how much this model was able to fit to the data. So when we had some, if we would add new observation there, you can understand that the model would probably then go more a bit towards that data point. And this now shows that these all 20 observations were kind of twisting the model towards those data points specifically, but there's a limitation how much they can fit because there's only 3 parameters in the model. And then that we can get the difference that the ELPD Lua is the unbiased estimate how well we could predict the future data, and this is biased estimate which is overfitted about this amount, which is limited by how many parameters we have. If we would have more parameters, we could fit more.
So in this case, it just happened to be that it's similar, close to 3, but how does one interpret that there will be, this is close to the number of parameters in the model?
So the question was that...
in this case, it just so happened that 2.7 is close to 3, but then generally speaking, how can we say that this number is going to be approximately the number of parameters?
So the question was that was it just by chance that this is close to 3? No, it's not just by chance. In models, parametric models, which are regular, non-singular models, theory says that this just happens asymptotically, and more data we have, closer we go, that this P-Lua would be closer to exactly to the number of parameters. With 20 observations, there's some variation, and it can be sometimes also that it's a bit over 3 with some realizations. But already with 20 observations, if you would repeat this simulation, you would have the difference still close to 3. And this is really about because of the how much the posterior distribution is fitting towards that specific data realization. And this is kind of the that for regular models, it asymptotically goes to this towards the total number of parameters, but in finite case, and specifically with the hierarchical models and non-parametric models and so on, it's not necessarily that this can be much less or much more, but I'll come back to these examples next week. But this is kind of the reasons why also originally, and also the information criteria are kind of one of the reasons why the logs scale is handy. We can also look at the, when I said that this is unbiased estimate of the predictive performance for new data, because we have a finite data, there's still some uncertainty. And we can also compute that uncertainty. So we can look at how much variation there is in these log scores. And if we take a standard deviation of those and multiply by square root of number of observations, we get what is the standard error. And so we would say that we can say that the log predictive density for new data is on average expected to be that, but this tells how much variation we would also expect to actually be if we would have a new infinite-sized new data. Because also if we would have just finite new data, there would be additional variation because of that. And there's a link, the references for reading more. And so the first reference is what's recommended for you to read instead of the 7.2. One thing is that now when we have this uncertainty, there's a bit of issue about what is the kind of what do we assume about observed data and what do we assume about the future data? And in the simulated data, I happen to have that these X values were on the fixed designed locations, shown with these dotted lines. And in that case, we don't have necessarily uncertainty. So if we would assume that we would get another 20 observations in these same locations, we don't have uncertainty about X. And now the uncertainty would be just that what would be the new Y values from this our generative process. But it might be also that the X's are also random in a way that we don't know what are the future X's. We are not modeling usually the distribution of X. We are usually making this only the conditional part of the model. But then, in this case, this SE would be related to also the uncertainty that we don't know actually also what are the future X values. And you could also handle coverage shift if you would assume that the future data distribution, especially the distribution of X's in the future is different, you could take into account. For example, if you do medical experiment, it's likely that you have actually selected somehow the population, the study population, or if you do it in certain region, and then you want to predict what happens in another region, and you might know that, okay, in that another region there are more older people. You could also take into account then in the predictions that how this distribution of X being different in the future affects your expected predictive accuracy. So the loop packets then shows this. It shows the computed from 4000 by 20 log likelihood matrix. So 4000 being the how many posterior draws we have, 20 being how many observations we have. We have the ELPD Lu estimate minus 29.5, the standard error, and it's also reporting this effective number of parameters PLU, which can be used as a diagnostic in problematic cases, but more about that the next week. There are some special kind of cases that when this cross-validation is applicable, and it's good to think about the kind of what does this mean that we have certain X values and what they might be in the future. Here's certain data sets, and we might make then a model. It says nonlinear model fit, and it is nonlinear, although it's very close to linear. And then we might want to then kind of predict what happens next. But it might be sometimes that actually all the future x's are beyond the data. And this is usual for time series data, for example. We've observed certain data in certain time points, and we want to predict for the future. And in that way, all the new dates, new x's, are something which we haven't observed before. And extrapolation is more difficult. So much more care needed, especially if we are extrapolating far away. We can extrapolate a little bit, but it's much more care needed when extrapolating far away. So can we then use cross-validation for these time series in a way that what happens if we remove some points? For example, leave an out. You can see now 4 cases where kind of the circled point would be something we've removed from the data. And in a way, the problem here is that with the leave and out is that it's easier to predict something from the middle of the time series because you know also where that time series continued after that point. This is still valid if you are interested specifically for what was the conditional model. So you would have some model for how the mean of the time series goes on, but at a certain point you have also some extra uncertainty that what you might observe, even if you could repeat kind of what happens in that same time point. And for that kind of the conditional distribution model assessment, this is still useful. But if we think that we would be interested in predicting like stock markets, we would like to be to something like this, where we leave future out so that we are using only the historical data, predict next time step, then add that to the data and predict next time step, add that to the data and predict next time step. And this way we are not able to use future data where the time series is going only past data. But still we are kind of repeating that how well we can predict just towards the future. So we are taking into account the special structure, the time series model here.
Do we start with the data with only one observation?
I would not start with just one observation. I would start with certain number of observations which is reasonable that we can, that specific model we want to fit. We could think that we are getting reasonable posterior distributions. And of course, it would depend on the model and the data that how much you would use from the beginning. And then you would start making these forward predictions. I'll come back to later what would happen if we would start just with the 0 and 1 and so on data points. We could also do m-step ahead predictions. This is common in like the electric demand prediction, that we want the electric companies need to predict electricity usage at least few hours ahead, and usually at least 24 hours ahead, because then there are some of the power plants are used only at certain points if there's predicted to be extra need for electricity. So you need to produce the same amount of electricity as is used. And so you can't have a power plant running if it's not needed. But then these extra power plants, it can take a few hours to start them. So you want to know beforehand when to start and optimize your electricity production. So m-step ahead is sensible also. Also for hierarchical data, we can take into account this hierarchical structure. And in a way that's showing that we can do different kind of things. So leave and out would be, again, reasonable if we are looking at that, what's that specific conditional part there. We could also do, in this case, it's predicting weight of rats. So it's measured at different age points, and we might be interested specifically in how well the model is able to predict in the future these rat weights, and then we could do, again, one step ahead modeling. We might do also just leave one time point out, leaving all the rats at a specific time point. Or we could do leave one rat out. So how well we can predict new rats based on the previous rats, but for all the time points. Or we could do how well we can predict rest of the weight curve given other rats and initial weight. So we have different ways of doing cross-validation. So you have to make some assumptions on data generating mechanism and use the knowledge of the prediction task if available. And there's also that, like my background was, there was emphasis that I wanted to know what is the predictive performance. But then there are also often cases that people are interested in scientific knowledge and then not necessarily making predictions with that model. And cross-validation can be used also in these cases to analyze how well kind of different parts, like in this rat weight example, there was also, are we predicting something specifically for the time model, or are we specifically how we can generalize from other rats to new rats? So different parts of the model can be analyzed also, even if those who are analyzing the kind of the rat weight curves would not specifically plan to use them in the future predicting rat weights. Running out time today, so I will continue with these cross-validation topics next week, so I don't need to hurry with this. The kind of the next part is then the kind of that in this already with 20 observations, if we would do the leave and out cross-validation, if we do it in naive way, we would need to run Stan 20 times. And then you've learned already about importance sampling, and then I will talk about Pareto-smoothed importance sampling leave and out cross-validation, how that can be used to speed up and how to diagnose it, and I also then discuss of these cross-validation things, and then also these model comparison selection will be also next week. You don't get new assignments yet, so in a way that you have time to listen also my next week lecture before having that exercise where you need to do model comparison. And then also next week there should be time for a bit more about the kind of discussing things you should have in your project work and discussing kind of bit of the project work presentation ideas. Questions?